What is up, boys, girls, ladies, gents, aliens, politicians, whatever category of life you fall into? It's this is Try Fail Repeat coming at you again with more nuclear stuff. Look, last time we talked about the SL1 reactor, experimental reactor that was being used back in the 60s or trying to be used, had a huge issue. That is a nuclear fission, or was a nuclear fission reactor. And in fact, all the reactors that we're currently using and have been using for power, electrical power, for since forever, have been what they call nuclear fission reactors. So, fission, you're taking a big atom, blasting it apart. It's decaying, it's falling apart. You're trying to get that to happen as much as you can to get as much heat as you can to boil water to turn a turbine. Uh, that's the normal type of nuclear power that everybody talks about, and in fact, that's the most efficient nuclear power we've been able to use so far, and we've been using it for a long time now. This video, actually, I saw that Tyler Folst did a reaction to this video, and I'm like, oh, I gotta take a look at this original video here. Um, I haven't watched either video yet, but this is actually from 3 years ago. I don't watch a lot of deGrasse Tyson. He's not really my cup of tea. I'll leave it at that. But I've seen so many clips of his stuff come out over the years. So it's fun to kind of react to him now. So let's get into this. This is I'll leave a link to the channel in the description and the original video. This is from Star Talk. How developments in nuclear fusion change everything, and this says big nuclear fusion announcement. So nuclear fusion is supposed to be the future. It's always supposed to be the future. Has been supposed to be been the future for the last I don't know how many years now, but it just really hasn't come to fruition, and I don't know that it ever will. Honestly, maybe at some point. We'll get into that. Let's see what this video has to offer here.
This will be a benchmark day. We'll look back on that fondly.
Benchmark
So, Chuck, what's been bugging you lately?
I'll tell you, I don't know if it's bugging me. Maybe I'm happy about it. maybe the entire human race has something to be hopeful about. You know how I feel about climate and the climate crisis.
Right.
But so I wake up this morning and it's all about.
Honestly, if we're worried about the climate crisis, can we please put more money into nuclear fission? I mean, nuclear fusion is fine. Sure, experimental research is fine, but nuclear fission, it takes so much money and so much time to actually get a nuclear fission reactor up, online. And if we just did that and made it easier and was, still kept it within the regulations and safety regulations, but made it easier to actually get this stuff operational, we could save we could do a lot for the environment compared to just burning coal. Coal power plants are extremely radioactive because coal tends to have a ton of radioactive material inside of it. Just the material they're taking in to burn has a ton of uranium already and other stuff inside of it that is really toxic to the environment and to people. And then you're burning the coal and you're getting carbon dioxide out and all that, and it's not great. So yeah, if we could just get more nuclear plants online, that'd be great. It's always a NIMBY issue. People don't want it, not in my backyard. They don't want it near them, right? But it has to go up somewhere, right? And Germany, they just recently, not that long ago, shut down all of their nuclear power plants and switched over to completely green energy, solar and wind. And now they're buying, I think, coal or natural gas from Russia because they don't have enough baseload energy generation to actually power their country. And yeah, shutting down all those nuclear fission plants was a huge mistake for them. So let's work on that, I think. I mean, it's fine to experiment and try and push nuclear energy forward, but we have plenty of safe options already for nuclear energy, and we're just not utilizing it properly. So, yeah.
Fusion everywhere. Everybody's talking about fusion. I'm like, whoa, Whoa, is this a good thing? Or are they yanking my chain? Are they just making me what are they doing? Are they doing the Lucy pull the football away from me? Or what are they doing? What is happening? What is happening with the fusion?
Oh, okay. So, the highlight is at one of the national laboratories, Lawrence Livermore National Laboratories, where they among all the national labs are one of their major tasks is as shepherds of our nuclear arsenal. Okay, the nuclear fuel, basically. So
Right, yeah.
radioactive materials that might be used in weapons, and it is funded by the Department of Energy, not the Department of Defense. So that in fact, the total amount of money we spend on defense is not only the DoD's budget, but an important fraction of the Department of Energy's budget that involves weaponry, basically. Okay.
Great, yeah.
So there, they have the world's most.
So what he's basically saying there, and that's a great point, because if I know what they're talking about here, this video was from 3 years ago. So if I know what they're talking about, it's probably the thing that they had happen at the National Ignition Facility, the NIF, which is part of Lawrence Livermore. They basically got the headline was they got more energy out of nuclear fusion than they put in, which is really twisting, really not mincing words, but really overlooking a lot of stuff there. So they take in a ton of energy and they use it to power these huge lasers to shove a little tiny target, little source into itself to kind of, what we talked about last time, implosion bombs, which for nuclear fission bombs, the implosion device, which has a bunch of conventional explosives and shoves a bunch of nuclear material together really in a really tight, tiny space. Here you're taking, instead of fission products or fission materials, you're taking fusion materials, which is basically just hydrogen and deuterium, and you're shoving that little tiny source into a little teensy bitty space using lasers to make it fuse. Instead of fission, you're trying to make it fusion. And when that happens, it can be a ton of energy out of it. But the thing is, they're calculating that, I think they were calculating that based off the amount of material they had and the amount of energy they were getting out. And it didn't take into account the lasers that were used, which was an immense amount of energy, like a ton of energy that with just to power the lasers to get this to work. So if you're using that sort of version of fusion, it's not really that efficient, especially not yet. Maybe it never will be, who knows? But this is not for, another point that he made there was, this is not for energy research. This is for defense research. Okay, this is the Department of Energy, because the Department of Energy is the Nuclear Regulatory Commission, and all of that stuff is all falls under the DOE, and they're researching nuclear fusion not for the commercial power grid. They're researching it because of nuclear weapons, because you can't really test nuclear weapons anymore. Back in the day, 40, 50, 60 years ago, you could just set off a nuclear weapon, in your own country, or I guess off a Pacific island somewhere, Bikini Island, Bikini Atoll, that kind of stuff. You could just set off nuclear weapons willy-nilly and nobody really gave a shit. Well, people gave a shit, but nobody was really trying to stop you. Nowadays, you can't really do a nuclear test. The different treaties that we have now prevent countries from doing nuclear testing using actual bombs. So now you have to use these sorts of experiments to sort of give you the results that you want without actually setting off a bomb. So, we've had nuclear fusion bombs. We've had those for quite a while, which again use nuclear fission to ignite the actual nuclear fusion, actually get it going, which then can set off a chain reaction of fission, fusion, fission, fusion, fission, fusion. But either way, we can't test those weapons anymore. So to be able to test stuff that has to do with fusion, you have to set up this huge lab to actually test basically one form of fusion. In this case, like I said, inertial confinement, which is the same sort of confinement. Which confinement is basically the way you're shoving everything together into one space to get it to fuse. It's the same kind of inertial confinement is the same thing that's used in the sun, except the sun doesn't use lasers; it uses gravity because it's fucking huge. So it's there are other projects. One called ITER that uses magnetic confinement. That's a whole other thing. But this is I'm pretty sure they're talking about the announcement that they got more energy out than they put in, which was bullshit. It's just basically bullshit, right? I mean, if you discount the lasers that they put where all the energy was put in, then yeah, they did. So that's cool. But we already know that can happen because the sun works. So it wasn't really like a big breakthrough. This is a breakthrough that they're kind of, I think, using as propaganda. But this is more just them testing nuclear weapon stuff and then using that as a way to say, oh, look at that, we did fusion. This is, it doesn't. All right. Anyway, sorry, getting a little off track here.
Powerful laser. And what they do with a bunch of these lasers.
What you want to do is save hundreds.
Oh, man, that's not what I want. I want to do lasers.
That's great.
I don't want insurance.
Ask your friend to stop.
Get out of here.
Lasers is they aim them all at a tiny target and they cause the target to explode. All right. That alone is not okay.
Sounds like America so far.
You'll say, well, what's new about this? Because we've been blowing shit up for like forever. So if the target is uniformly heated, evenly in all directions, and the material is very uniform in all directions, so there would be a spherical shape, then the explosion creates an implosion on the other side of that explosion. Right? You can't just have stuff come out unless the Newton's law for every action is
which is, well, so yeah, like the sun, you're having an expulsion of energy, of course, but it's not really an explosion inside the core. It's mostly just it works its way out. But it's with that, it's not using lasers. Like I said, it's using gravity. In this case, you're using lasers to shove everything together. But like with a nuclear bomb, a fusion bomb, a thermonuclear device, you're using the implosion that comes from the explosion of the fission bomb to then create the conditions for fusion, which then creates even more energy and gives you this sort of runaway reaction. But yeah, so that's pretty much right. That's pretty much good what's going on there.
An opposite reaction. So
reaction.
The explosion that comes out creates an explosion that points inward.
Okay.
And that creates very high pressure and very high temperature. And under those conditions, you can take two atoms, light atoms, and merge them into a heavier atom.
Sweet.
That takes a lot of high temperature to accomplish. Because let's take the lightest atom of them all.
If you go back,
merge them into a heavier atom.
Okay.
Sorry, if you go back here a little bit,
very high pressure and very high temperature. And under those,
so what you see there. So this is the H stands for hydrogen. This is an element. This is the lightest element there is. It's very abundant in the universe. This is the most abundant element in the universe. But this, you've got the red thing is a proton. The green thing is a neutron. Protons positively charged. The proton is what determines the element. So hydrogen will always have one proton. But here, these are isotopes of hydrogen. So hydrogen, the stable form of hydrogen, has no neutrons. It doesn't need it. It has one proton, one electron. These are isotopes. So they have, this one here is 2. The 2 means that's the atomic mass. So that, or the atomic weight or atomic mass, whatever the mass number. So you've got 2 subatomic particles. You've got a proton and a neutron. That gives you 2. With this is just a notation for it. This is actually called deuterium. So you've got a proton and a neutron together, and you don't need that neutron, so it makes it radioactive. It's unstable. It will decay over time. With the 3 over here, you've got a proton and 2 neutrons. This is called tritium. It definitely doesn't need those neutrons, and it is very much more radioactive. Tritium is very radioactive compared to deuterium. Deuterium is, hydrogen, normal, just one H, just normal hydrogen, isn't classically what we think of as radioactive. It will, over time, that proton will eventually decay, but that's a whole other, and that could be trillions of years in the future. That's a whole other thing compared to this. This is actually this is a semi-stable isotope that is trying to just get rid of that extra mass that it doesn't need to make it more stable. So deuterium, tritium, this is what they're using in when they use at ITER, and this happens in the core of the sun. But at ITER, where they're trying to test the magnetic confinement fusion reaction, that's what they're going to use. In this case, at the National Ignition Facility, they're using deuterium and tritium, and they're just kind of shoving them down to this really tiny space and hoping that that will cause the fusion that they're looking for and put out a bunch of energy. Like I said, though, if you're using a bunch of really powerful lasers to do that, you're using a lot more energy than you're actually than just the energy of these couple little isotopes here. So it's not really that meaningful for actual like fusion energy, electricity generation. This is just this is for weapons research, but this is what they're doing here. So that's kind of the concept. You can see with helium, you need, so they're what they're doing is they're fusing these together instead of splitting atoms apart with fission. They're fusing these atoms together, these isotopes here. So you've got two protons. So with, like I said, hydrogen is generally one proton. These have extra neutrons. Helium, stable helium, is two protons, two neutrons, and two electrons. But what you're getting here, you actually have five subatomic particles. You've got two protons, three neutrons. You're combining these together, and you're getting helium because you're getting helium and one extra neutron. So that neutron is going to get kicked out, and it's going to do its thing, whatever, somewhere else. But you're taking this and making helium from it, and in the process, you're actually putting out energy, a lot of energy, more than fission, because just that hydrogen itself has there's energy within it, and then getting this to actually convert into a stable isotope of helium, it's actually going to a lower energy state, which is more stable, and so it doesn't need that extra energy, and it will just expel it out. And this is a sort of example of mass to energy conversion, which E equals mc squared. If you have a little bit of mass times the speed of light squared, it's going to give you quite a bit of energy, right? So that's sort of the idea here.
Conditions, you can take two atoms, light atoms,
Right.
and merge
Right.
them into a heavier atom.
Sweet.
That takes a lot of high temperature to accomplish. Because
Right.
let's take the lightest atom of them all, which is what?
I don't know, maybe hydrogen?
Hydrogen, you got it. So hydrogen in its nucleus has one proton.
Right.
And helium in its nucleus has two protons plus
Right.
two neutrons. So how am I going to create a helium atom from a hydrogen atom? So you got to get a bunch of hydrogen atoms together. All right?
Together.
Well, here's what no one is telling you in the news, but it's obvious when you think about it. What do two protons want to normally do? They're
Well,
both
they're
positive charge.
repel.
They like each other, but they don't like each other because they're alike.
Chuck.
Okay.
I love Chuck.
It's like when you meet somebody at a cocktail party and they remind you of yourself, and you're just like, I don't like that dude. I don't really like.
That's a
that.
great
I don't want to
analogy.
be over there talking to that dude.
Chuck is still in
That's my
therapy,
proton-
people, just so
my
you know.
proton- I know, exactly. It's like, it's a simple question, Chuck. Where did cocktail parties and liking people come in? Yeah, but they want to get away from each other, right?
So these are like charges. So in the case of two protons, they repel each
Right.
other. So
Right.
how do you get them to come together as a new helium nucleus if they want to repel? So this is like rolling a ball up a hill. All right. If you don't give it enough energy, it's not going to reach the top. It's not going to reach the top. Okay.
There you
But
go. So, yeah.
if you roll it fast
This is called the Coulomb force, which has to do with the electromagnetic force. So there are four fundamental forces: gravity, uh, the electromagnetic force, the strong force, and the weak nuclear force. So the weak force is the thing that causes big atoms, big nuclei to fall apart, to split, because these things are trying to. They don't have enough stuff in there to actually make them stable, so they will end up kicking things out and that sort of thing, and so they'll be kicking neutrons out and that sort of thing. With this, you're trying to overcome the electromagnetic force, shoving two protons together, or which the Coulomb force they call it, and they want to repel. So you're trying to shove them together to overcome that force, enough to overcome that force, so that the strong nuclear force actually kicks in, and they stick together, they fuse, and that's sort of where you're at there. Yeah, that's so far. This is good explanation.
And faster, giving it more and more energy. Eventually, the ball will reach the top and tip and go over and fall on the other side of the hill.
Paramount Plus is now the home of all your
Sorry.
favorites.
Got an ad.
Plus a whole
My bad. I'm just recording my screen of this YouTube account, which has ads, so you just gotta deal with it.
Y'all are good together.
You probably got ads on your side too. It's just the way it is. And okay, there we go.
That is precisely what's going on with
YouTube's
two
got to
protons.
get paid.
Here it goes. The two protons want to come near each other, but they repel. Let's boost the temperature, which speeds everything up. They get closer to each other before they repel. Boost the temperature some more. They get even closer. There is a magic temperature at which these protons.
By the way, temperature essentially just energy. Temperature and energy are not exactly the same thing. Energy is sort of this mystical thing that we talk about that isn't. We don't really have a great definition for what energy is, but it is a thing. But temperature is basically how much particles are moving inside of something. It's sort of the measurement of how much something is moving around. Absolute zero, lowest temperature you could possibly ever reach, although you can't really reach it because you will always have some movement somewhere. Absolute zero is sort of unachievable. But energy is it's sort of the amount of work that you can get out of something, so what you can use to do some amount of work. But we don't, at a fundamental level, we don't really understand what energy actually is, if you will. It's sort of a mystical sort of term that we just apply to something that we can observe. So that's energy. But yeah. So when he says temperature, there, he pretty much means energy. But yeah,
will come close enough so that an entire new force operates. It would have to be a strong force in the nucleus to keep two protons together. In fact, the name of that
quantum love. That's called quantum love.
Where's that disco? So I remember Jungle Love. Remember Jungle Love? We know Quantum Love.
Oh, Jungle Love.
Yeah, Quantum Love is like
Quantum
you resist
love.
until you cross over the barrier, and then you're there. So when they cross that barrier, a strong force that operates in the nucleus takes over. It's one of the fundamental forces of nature, and it's called the strong nuclear force. There it is. Okay. That's what it's called. It is a very short range force. It only operates on scales as small as the nucleus itself.
Wow.
But you have to get.
Same as the weak forces also operates on very small scales. Well, so does the electromagnetic force, but it's those sorts of scales are a little more observable by humans. But the strong force and the weak force operate on the scales of atoms, and in fact, the strong force is what holds quarks together within protons and neutrons, but it also is what holds neutrons and protons and all that together in the nucleus. But then once you get a big enough spacing between those particles within the nucleus, you can actually, or those subatomic particles, you can actually end up with the weak nuclear force, be overcoming that strong nuclear force. So it's sort of it actually the force carrier for the strong force is called the gluon because it sort of glues everything together. The what are the force carriers for the weak nuclear force are like the W boson and the Z boson, which those are that's a whole other topic, but those are the things that sort of end up kicking the particles out of the nucleus and causing it to split apart because now you've got a repulsion between the protons and it breaks apart. And yeah, it's a whole that's a whole thing. There are probably a dozen college classes, that physics classes that discuss how those forces in themselves actually operate. It is very complicated stuff. It all has to do with quantum mechanics and all that stuff. I'm not going to talk about all that, but yeah. So you've got these two forces that sort of operate on the scale of an atomic nucleus, and the strong and weak nuclear force, and then you've got electromagnetism, which works at a it works at also a pretty small scale, but it also you can see the effects at a pretty big scale. You can't really see the effects of the strong or weak nuclear force at a big scale because you can't really see atoms and that kind of thing. You can see the what atoms add up to be, but you can't really see what they are. But magnets, you can see what they add up to be, but you can also see that force, really affecting stuff. And then gravity works on even bigger scales. We don't even in quantum mechanics they don't even discuss gravity because it is so much weaker than even the electromagnetic force that it isn't even really a thing. Although that's where you get sort of grand unification where they're trying to combine all of the four fundamental forces into one thing so that they can understand how the universe works on a grand scale. But that's all again more outside the scope of this video. We're just trying to get through this nuclear fusion thing.
There for it to grab a hold of you and make a new atom. That's why it takes high density, high pressure, and high.
Sorry, I if you if you notice a jump in the video there, I had to go to the bathroom so bad. So I just realized how bad I had to pee. So I had to get up and go to the bathroom. I paused the recording and then I forgot to pause the actual video, but it only skipped ahead by like a second or two. So I'll just continue here.
I'm with you.
That is thermonuclear fusion. Thermo is hot. Nuclear is the nucleus.
Right.
Fusion, they're bringing it together.
It's all pretty hot. Even nuclear fission is pretty. In fact, that's how nuclear, thermonuclear bombs work. You have to have a really hot and compacted environment to get nuclear fusion to actually work then. But yeah, even nuclear fission is unbelievably hot. We're talking millions of degrees. So it's, but yeah, it's all hot. But yeah, the idea of a thermonuclear bomb is where you start fusion due to the heat from fission. So that's why they call it thermonuclear. It's kind of a nebulous term. It doesn't necessarily mean anything on its own, but once you kind of explain it, that's sort of the idea of it. And we came up with thermonuclear bombs a long time ago. We just haven't been able to do the same thing with nuclear reactors. We've only been able to make fission reactors. We still haven't been able to make fusion reactors. So
turns out that when you do that, your products have less mass than when you started with.
Whoa!
Oh my gosh. Where did the mass go?
that is true. If you actually look at a periodic table and you look at the atomic weights or the atomic mass or whatever, the two hydrogen atoms, or in this case, a deuterium atom and a tritium atom, they will have, if you look at their weights or their mass combined, it will weigh more than one helium-4 atom. So a helium atom that is the isotope of helium that is stable, that has 2 protons, 2 neutrons, those 2 hydrogen atoms will weigh less than that helium atom because the helium atom is more stable in that configuration and doesn't have as much overall energy trapped within it. So that energy gets released, and it's quite a bit of energy. It's quite more than fission will release.
Exactly.
E equals mc squared. My
energy.
lovely. So
MC
the
squared.
mass on the one side of the equation, if you lose it, it manifests on the
Let's go
other
back to
side of the
Einstein.
equation as energy.
There you go.
There it is. And so they manage.
And the reason it's so big is because you have E equals mc squared is energy equals mass times the speed of light squared. The speed of light is huge. Okay, so you're measuring mass. Blah, 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 I can't talk. You're measuring mass in kilograms. The speed of light is measured in meters per second, and so you are taking this speed, and the speed of light is so the mass in kilograms of protons and neutrons is extremely small, right? Very, very, very small. I think it's on the order of like 10 to the negative 9 or 10 to the negative 10 kilograms or 10 to the negative 12 kilograms, something like that. But the speed of light is 10 to the 8th power, right? Meters per second. And then you're squaring that. So you're talking about something very small over here to 10 to the negative whatever, negative 12, let's say, times 10 to the 16th. So you're getting a huge amount of energy out of that. Now the energy is measured in again, it's going to be overall, it's going to be a pretty small amount of energy, but when you have a ton of that happening every second, it adds up quite a bit. So that's the idea. So you're going to get more energy out of it than you put in, assuming you don't have to power some extreme lasers or something like that. If you can limit the amount of power that you have to put in to create the conditions for fusion, which I still don't know if it's actually possible at a human scale. Like I said, the sun does fusion, nuclear bombs do fusion through nuclear fission, but they do fusion through nuclear fission, but on this sort of safe, low energy sort of scale, to do that, you have to essentially put in a ton of energy from somewhere else, and it just doesn't. I don't think it scales well. I really don't. I don't think that we'll ever see nuclear fusion. We won't. I don't think we'll see it in our lifetime for sure. Will we ever see it actually operational at a sort of a commercial nuclear reactor level? Maybe. It's really hard to say. But yeah.
So at the Lawrence Livermore Laboratories using lasers, and by the way,
And the reason that fusion is so sought after, not just because there's a big increase in the amount of energy that you're seeing from it versus fission, but with fission, you have to put in products or you have to put in reactants that are pretty rare. I mean, there's quite a bit of uranium in the Earth's crust. Now, uranium's weird. It's a big heavy element, but you think it would fall through the crust and get into the mantle, and we wouldn't be able to get to it. But in fact, the mantle, it doesn't play well with the geometries and physics of the mantle, so it actually gets pushed back out into the crust. So we have a lot of uranium in the Earth's crust, so we can actually access it actually pretty close to the surface. So we can actually access it pretty easily. Plutonium is another radioactive fission fuel, but it is not natural, so it's actually synthetic. We have to make it taking uranium and creating what's called a breeder reactor, actually breeding sort of certain isotopes of uranium into plutonium, which is going to decay and we won't be able to get back after so long. But it is pretty similar to uranium in its half-life and all that, and its weight, but it's not something that you find naturally in the Earth's crust. You can only find really uranium, and then you use the uranium to create plutonium, and you can create other types of bombs, or in fact, other types of reactors that use different parameters. But yeah, you're not really, mainly it's uranium, and you're always going to have uranium mostly involved. Sometimes thorium, but that's a whole other thing. That's mainly for breeding, not for actual fuel. But those elements are relatively rare within the Earth's crust. I mean, they're pretty abundant because the Earth's crust is huge, but they're relatively rare compared to other elements. So, especially compared to hydrogen, and even deuterium and tritium, which are much rarer than just hydrogen, they're still pretty abundant because hydrogen is the most abundant element in the universe. So, even if you had to, siphon that hydrogen out to find the deuterium and tritium, it's still abundant enough that you can get it. Versus uranium, it's even rarer because there might be a lot of it in the Earth's crust, but it's just we've got a limited supply of it, so we can't run fission forever. At some point, we're going to have to move on from all the fossil fuel stuff because that's going to run out, and even the fission stuff because that's going to run out. So fusion is kind of necessary. We kind of need it. We kind of need to get there, but I don't know that we ever are anytime soon. It is extremely hard and energy intensive to actually create the conditions for fusion to be efficient as an energy source. So, yeah.
Led the world in lasers like for decades. In fact, people on the inside call it lasers, and lasers. Okay, Lawrence Livermore National Lab. Okay,
lasers, and lasers.
It's kind of funny, actually.
Right. So anyhow,
lasers
they
are
have
complicated,
managed
especially
to
big ones like
add up
that.
how much energy it takes to turn on the lasers and fire them, and then look at how much energy comes out after you've done this. And they got 50% more energy out of this than the energy of the lasers that went into it.
Paramount Plus.
No, they didn't. No. So, sorry, we've got a Paramount Plus ad here. No, we didn't get 50% more energy out than the lasers that we put into it. That's the problem. We got 50% more energy out than the energy equivalent of the mass that was put into it, which was significant. If those numbers are right, that's significant, right? Because we got more energy out than the mass we actually put in, which the energy equivalent of that. But the energy that was put into the lasers was far exceeded the energy that we got out of this experiment or this result. And so, yeah, that's complete bullshit. Whatever he just said there, that is complete bullshit. That's the thing. They put out this sort of headline. It almost seemed like propaganda. They were trying to say like, "Yay, we did this fusion breakthrough," but they really didn't. Is it significant? It's significant, right? It's significant on a certain scale, but the process that they did, in fact, the ITER experiment is actually going to be the experimental reactor is going to use magnetic confinement because it's way more efficient than laser confinement. So, yeah, I don't know. No, Neil. God damn it. Nah.
Now the home of all
Let's
your
get through this ad real quick.
What? Plus a whole new world of original series, movies, and live sports.
This takes us to the next level.
New home, same family.
Y'all are good together.
Paramount Plus. Subscribe now.
Wait.
That's amazing.
Amazing. First time that's ever happened.
Now that's an energy source now because you got more out than you got in.
Again, no, that's not what actually happened. So keep in mind, Neil is completely misinterpreting the results here. He does this. He doesn't. I don't want to say he misinterprets the results incorrectly all the time. But Neil tends to talk about stuff that's way outside of his field. Again, I'm not a scientist, so I can't say that I have a certain field that I'm an expert in or anything like that. But he tends to be a little more sensationalist about stuff and tends to, I think, pretend to know more about certain things than he actually does. He's an astrophysicist. He's done a lot of good work in astrophysics, but he's not a nuclear expert. And on this, he is 100% wrong. This is pretty bad.
Which is
Correct.
what I want to know. Which is so. What did it take? What would it be? What did it measure? Like, is it anything significant? Percentage-wise, that's great. But, like, what would it take to turn
It would
this
have
into
been great
an
if
energy?
it just broke even. That would be a major
that's true.
milestone unto itself, right? But the fact that
Right.
they got 50% more energy out than they put in, it says, oh my gosh, we can get the physics to succeed. And
Right.
for my money, I'm saying if the physics works, then it's just a matter of time before engineers say, I got this. I'm gonna make something out of that. I got this. And so
Again, he's talking about nuclear fusion research for bombs, nuclear weapons. So he kind of got it right in the beginning, where this isn't a research project for nuclear energy, and then he completely flubbed it, saying that they got more energy out than they put in. They put in way more energy overall than they actually got out. When you take into account how much mass they put in versus how much energy they got out of that mass, they got significantly more than they ever have. In fact, they went farther than the breaking even. They got 50% more than they actually put in, that's a great result. That's significant. Unfortunately, it doesn't account for the lasers that were used to actually create the conditions for fusion. So, oh, Neil, fuck. He completely fucked up here. Again, this is from 3 years ago. This is when this quote unquote breakthrough first happened. This was pretty big in the news. No one understood what the hell they were talking about, and so they just ran with these headlines of fusion working, blah, and no one realized that this was not ever meant for energy production or for electricity production. Then just this was for weapons testing. Again, the U.S. isn't really building a bunch of new nuclear weapons, but they still, in the event that they need to, they still want to understand what's going on with those weapons and do research on it, and they can no longer test those weapons, so they are using these experiments to sort of mess around with fusion. And is the result significant? Yes. Could it be used for, more research into electricity production? Yes. Is it more useful for weapon production? I would argue so. So that's kind of the point of this whole experiment. So, this isn't an experiment into energy production or electricity production. This is an experiment into weapons production. So, fuck. This is what pisses me off about these types of videos. Anyway, I've gone on now. What is this? 6 times longer than the actual how much video I've watched. So I just keep rambling on about this stuff. But I'm not super up on what the design of fusion reactors and all that. But I apparently understand more about what's going on here than a goddamn astrophysicist. So take that for what you will.
Amazing.
Yeah, and so I'm very much look forward. There's a civilization pivoting on this result. And by the way, what
It's
I just
not.
described,
This is
the
not.
sun does.
This is not pivotal at all. This is not a pivotal result. This is a marginal result. They are doing. They're getting results, which is good, but this is not pivotal. This is not the world is suddenly going to switch over to fusion energy. The world can barely survive fission energy. Imagine trying to convert everything over to fusion energy, where you have to put in, like 1,000 times more energy than you're getting out. That's pretty much what he's saying here. Oh, man.
Every moment of its life. The problem over all these years is that, of course, we've known how to make fusion.
Mm-hmm.
We've known how to make fusion since 1949 or something. When the first fusion bombs were called hydrogen bombs. They're using hydrogen. That's what I just told you. We have 2 protons is merging hydrogen atoms, nuclei together.
And again, they're using fission bombs to ignite those fusion bombs. Which, if you consider how much energy is in a fission bomb, I think they're using even less energy here for the lasers than a fission bomb. But still, they're using a significant percentage of a fission bomb's energy from the power grid into the lasers to get this fusion reaction to happen. And it's putting out a very minuscule amount of energy, but more energy than they were trying to fuse but not as much energy as was actually going into the whole system. I hope that makes sense. I hope I'm saying, I hope I'm getting that point across, because this was not a breakthrough. This was not pivotal. This was an incremental thing. Very small update from what we were already doing into another sort of iteration of it. We're more likely to see good results from the ITER project. You'll have to look that up, IATR. Just Google ITER fusion. You'll see this massive reactor that they're still building to try and just do research on fusion to see if it's even feasible for commercial energy production, which, again, probably not going to happen in our lifetimes. Might not ever happen. We might always need fission or something gravitationally as massive as the sun to get fusion to happen efficiently. So it's this is, yeah, we'll see. Again, this was 3 years ago. So we'll see how far this goes from here. I doubt we're going to see any results from that. Probably more, from ITER, but ITER is still under construction. So
we've known how to make fusion forever. The challenge is not how do you make fusion, how do you control it?
Yeah, because you don't want the
that's not the challenge at all, actually. We know how to control it. We don't know how to get it started and keep it going without putting in more energy than we can get out of it in total. In net energy, right? That's the idea here. Gross energy, you're talking about just the fusion, like I could say I made $1 million last year, right? I made $1 million gross. So I made $1 million gross profit, right? Or say $1 million revenue. Well, how much did you put in to make that $1 million? What were your expenses? Well, my expenses were $1 billion. So, gross, I made $1 million. Net, I made negative $999 million. Well, that's not efficient at all. Who's going to fund that, right? And no one. No venture capitalist is going to come along and say, "Oh yeah, that's a great margin. Go ahead and I'll fund you, give you all the money you want." Of course, because that's the problem here. We're talking about revenue versus profit. We're talking about gross profit versus net profit, or gross margin versus net margin, right? So this is production before expense. That's what we're talking about here. And Neil is not hitting this point correctly, and it's really sad because he should know better, but he's a sensationalist. He's a more of a science communicator than a scientist anymore. And science communicators tend to be very very headline based. They will look at the headline and say, "Wow, that's amazing," and never actually deep dive into the reality of what was done or what was achieved. And that's honestly kind of sad. It sucks.
company having to move to a new city because there's no city left.
Right, exactly. So while in America, we're really good at blowing stuff up, we're less good at controlling that explosion, right? So
I will agree with him there. America's great at blowing stuff up, but actually controlling the explosions and turning them into legitimate use. If America could get better at actually building and utilizing nuclear fission, and instead of focusing on nuclear weapons research, which involves nuclear fusion, it would be far better off. We would be net zero as far as like carbon production goes. We would be net zero, even like negative. We could easily surpass all other countries in controlling fossil fuel output, but we just don't want to. We honestly don't want to. No one seems to want to. But right now we're starting up all these AI data centers, which are sucking up all this energy and water, generating massive amounts of terrible CO2 and destroying the environment, and also, sucking up all the potable water and all that to run them, all so you can, watch a cat eat an alligator or something. I don't know. I just like, where you can watch Neil deGrasse Tyson box an alligator. So I mean, this is kind of what we're doing right now. With these AI data centers, and uh, like, but yeah. So man.
The holy grail was, can we undergo fusion in a controlled way where one day you might be able to throttle it or contain it or transport it? And
Sure.
we'll finally get
Sure.
maybe that ending scene in Back to the Future.
Right.
Here's your cue, Doc.
Marty! It's your kids, Marty!
I love Chuck. Oh my
And
god!
do you remember
I love Chuck.
how,
Oh!
and Marty says, yeah, but Doc, where are you going to get the energy? There's no lightning bolt, and there's no room for, what are you going to do? And remember what he does?
He dumps a bunch of trash into the flux capacitor, which is now powered
96
by
gigawatts
fusion.
or whatever the hell it is.
Mr. Home Fusion, right? It was like a blender.
That's right.
He puts it in, and that undergoes nuclear fusion. And so one day, perhaps, we have fusion reactors in every car. And then you could
Wow.
there it is. So
That is a huge leap forward. I mean, maybe one day is doing a lot of heavy lifting there. A fusion reactor at this point, an actual fusion reactor. So when we talk about these lasers that they're using at the National Ignition Facility at the Lawrence Livermore Labs, we're talking about these lasers are, how old computers, how you have a computer now, it sits on your desk, or even your phone that's in your pocket. Computers used to be the size of rooms, giant rooms. This would be a computer. The lasers they're using for this nuclear fusion are the same sort of scale. They are giant rooms of stuff that's taking an actual sort of laser source and focusing that down into all this little stuff, and then you've got rooms and rooms and rooms of these lasers, and you've got to essentially put all of this stuff. That's laser inertial confinement, not magnetic confinement. Magnetic confinement is probably more scalable, but you're talking about, if you look at the ITER project, ITER again, look at that project. It is a massive building. Imagine squeezing all that down into the size of a car engine. Yeah. So how long did it take us to go from computers that were the size of rooms, giant buildings, into, the form factor we see now sitting on a desk or in your pocket as like a smartphone? It took decades and decades. And I think it's going to be even harder, because here you're talking about putting a ton of energy into something to create the conditions that are right for fusion, which takes a lot of heat and a lot of pressure. And it's not feasible. I hate to say that we're on the verge of something that just isn't going to work, but that's what it feels like. We're on the verge of a breakthrough that just isn't going to get us anywhere. According to Neil, we've already made that breakthrough, but we definitely haven't. We definitely haven't. So want to get that across. We definitely haven't made that breakthrough. So, seeing him talk like this just pisses me off a little bit. We haven't come anywhere close to that breakthrough. So if we could do cold fusion, that would be a whole other thing. Remember cold fusion? This was a thing a number of years ago that people thought might have been real, and they came up with a whole thing and kind of faked the data and were like, yeah, it's real, this is real. The thing is that cold fusion, if you can contain the actual, radiation from it, cold fusion could be an extremely viable source of energy. But as far as we can tell, cold fusion is just not possible. And yeah, this is not cold fusion. This is the opposite of that. This is hot fusion, and it takes a lot of heat, a lot of pressure, and it is not scalable on the size of cars, almost for sure. I don't think you could ever get it down the size of cars. Again, we like to think in this sort of sci-fi way, like in the future, we're going to be able to just put a fusion core inside, like Fallout. You're playing the game Fallout. We can put a fusion core inside of someone's backpack, and they're in power armor, and they can do whatever, blah blah blah. But that's just not how it works. That's sci-fi. I mean, that's almost science fantasy, not science fiction, but science fantasy. It's just not possible because it takes a lot more work to actually contain it and control, and it's a lot of heat. And can you imagine the heat that you get from internal combustion engine is quite significant. Can you imagine the heat that you get from a nuclear core? It is I say substantial. It is a lot of heat. And you're also getting a lot of like stray neutrons just flying off without any shielding. So, oh man, this is so outside the realm of possibility at this point that it is beyond science fiction right now. It might as well be called science fantasy. This is like Star Wars tech. There's absolutely no fucking way. Good fucking luck. Let's get through the rest of this video. But Jesus, this is pretty sad.
This would transform civilization.
It would. Yeah, it would.
Regardless of the carbon footprint that it doesn't have, it would transform civilization. But it also happens to not have a carbon footprint. So
nuclear fission has a very small carbon footprint. It's mostly like the carbon footprint of the vehicles and operations that it needs to build a fission reactor. Fusion has probably the same carbon footprint as nuclear fission, but you don't need all of the nuclear material that's like hyper radioactive and radioactive for billions of years. It is a lot less than that. It's mainly just sort of almost just hydrogen, kind of like just water. It's very simple stuff. But getting all that stuff can cost a lot of energy. So if you don't already have fusion to get that, then you're putting a lot of energy into that. And, ITER is already using, I think it was like a third of the tritium that's available in the entire world. So just for the tritium, you need like a third of the third of the tritium that's available around the world. So tritium isn't that common; it's pretty rare, and it's highly radioactive. So, maybe it's a little safer than nuclear fission because you can't have a meltdown in a nuclear fusion reactor, but that's about it. I mean, it's still pretty energy intensive, and where are you getting that energy from? Are you getting it completely from solar and wind, or are you getting it from nuclear fission, or are you getting it from coal and natural gas? Like what? So yeah, I love the idea they're thinking about the environment, but we're already so far past that point, talking about putting it into cars and stuff. Like a goddamn Fallout game. Oh boy.
Stave off this growth of fossil fuel burning and greenhouse gases, and we'll still have to recover from the damage we've already done because a lot of the carbon dioxide got took into the oceans. And if you start removing it from the atmosphere, it begins to come out of the oceans.
Sure.
And it'll do that until it becomes equal again. So you got to recover that. But it is the future. And
if you had this sort of energy, you could essentially pull that extra carbon from the oceans with that energy. But we're not going to have nuclear fusion anytime soon. So we're not going to be able to recover that. So that is looking beyond the scale of getting nuclear energy or nuclear fusion energy. We're looking well beyond that into developing technologies to pull carbon and all out of the oceans to help the oceans recover. That's well beyond the scope of just getting nuclear energy or nuclear fusion.
I tip my hat to this science
Gotta try
physicists
and get
and
through this.
engineers
I'm almost to
at
an
the
hour
national
now.
labs And this whole thing was important enough. It was a press conference announced by the Secretary of Energy. So, oh yeah, we're chomping at the bit.
Propaganda.
So
All
then it
propaganda.
is good news.
Good news. You
I
suspected accurately. Yes.
all right.
And we've been at it for decades. Just thought I'd tell you that.
Yeah, of course we have.
And so this will be a benchmark.
Been doing
day.
nuclear weapons for multiple decades.
First and second week of December in the year 2022. We'll look back on that fond
Another
period.
day in December
This is
that will live
2022.
not in infamy. What is it when it's a good thing?
Femi.
Just Femi.
That's hilarious. That's a good question. And live in infamy, live in fammy. Ew. Yeah, it doesn't really make much sense. But okay, yeah.
Femi. Okay. All right, Chuck, we got to end it there.
All right.
All right, but there's way more about like fusion. That's another show. We'll talk about stars.
Yeah.
There's
should
more
do that.
and why stars explode. All right,
Yeah.
I'll leave a teaser here. You ready? Fusion, you get energy by combining little atoms. Fission, you get energy by splitting big atoms.
Okay.
But wait a minute. There's got to be some point in the middle where these two phenomenon meet.
Ooh.
What happens then? Therein are the seeds of the undoing of great massive stars in the universe. That's a whole other explainer we'll get to.
That's a great.
Nuclear fusion
Right.
Okay.
in a nutshell. This has been yet another Star Trek
Because a
explainer.
lot. So stars work on the process essentially of mostly fusion. I don't know that stars work on the process of fission, but a lot of stars work. So most stars, they will create like up to I think it's iron is what they get up to iron, and then they stop being able to fuse stuff together. Gold is created. Gold is heavier than iron. I think iron is like atomic number 56, I want to say. Gold is like 83. So, how do you get gold if things aren't getting fused past iron, right? So if these stars are, and it all comes essentially from supernovae, that kind of stuff, stars exploding, that sort of thing. It all comes from that, where you've got this intense amount of energy and pressure fusing things way past iron, but that stars can't maintain. So all this uranium that we have on the Earth mainly comes from supernovae. It doesn't come from stars at all. Which the hydrogen, the helium. Well, the hydrogen has been there for pretty much since the beginning of the universe, but the helium, the carbon, nitrogen, oxygen, all that stuff is coming from stars, right? But where are we getting the really heavy elements from? Past iron, it's mainly from stars exploding, which don't happen that often. But there are so many stars in the universe that, of course, over time, billions of years, you're going to get enough stuff to form and give you that kind of stuff here on the Earth. So really cool stuff. This is awesome. I love this kind of stuff. But yeah, Neil was completely wrong here on the fact that this is a breakthrough. This is not a pivotal moment in human history. It is an incremental. It's kind of like with batteries. It's an incremental step to getting to batteries that are actually really fucking good. We're getting there. We're not quite there, but we're getting there. Can we ever really get there? Well, I guess we'll see. I have no idea. But yeah, thanks to Star Talk for the video. This is just another reaction to another nuclear reaction. The last one was a disaster. This one, sort of a breakthrough. It depends on how you want to define breakthrough. More of a nuclear weapons breakthrough. Not really a breakthrough, but just another nuclear weapons experiment. Essentially, this wasn't really a breakthrough in nuclear physics, but this is cool stuff. I'm not trying to downplay it. This is cool stuff. It's cool. They got more energy out from the amount of mass that they were able to compress and put into this space, but the energy that they put into the total laser system was far exceeded the amount of energy from the mass that they put into it. So it wasn't like a nuclear, this wasn't the nuclear candle being lit, you know. This was a very small increment in the nuclear, sort of the nuclear ladder. Uh, so the small, this is a tiny rung in the nuclear ladder. Um, it's cool, yes, but the headlines are making it out, or were back in 2022. They were making it out to be far more than it actually was, and they weren't taking anything realistic into account. Unfortunately, Neil fell into that trap, as he does quite often, sadly. But yeah, I appreciate the video. I appreciate Chuck, Chuck over there, just asking questions, doing his thing. I like the fact that Chuck is kind of the guy that's like, Neil's supposed to be the expert, and Chuck is supposed to be the guy that's like a complete dummy who's just asking questions like, I don't know, what does this do? What did that do? And Neil's sort of supposed to be the one that's sort of answering all that. Neil gets stuff right. He gets it right a decent amount of the time, but like there's times that he's just not. He's completely off basis, has no idea what he's talking about. But in this case, completely wrong. Not completely wrong, but he talked about other stuff that didn't have to do with this exact experiment, where he was correct about, but this experiment was not a giant step forward in nuclear fusion. It was a very small step, and we're going to have to go through a lot more stuff to actually get to a really big step. And I'm hoping for that day. I mean, if anyone wants to get to nuclear fusion, it's me. But are we actually any closer? A little teeny bit, we're kind of closer. I mean, we're getting there. So it's, that's a good thing. But it's not like the headlines. You have to remember that science doesn't work off of headlines. Science works off of data, results, experiments. How much time and money do we have to put into something? And in this case, it's a lot of money because it's a lot of energy going from the grid into these lasers, into these nuclear sources. And yeah, it's a lot. It really is. You're creating essentially the conditions of the sun ish in this, tiny little chamber that, you're shoving all these lasers into. So is it worth it? I think it is. I think we should still keep doing this kind of stuff. But is it actually like changing humanity? No, unfortunately not. Does it help the research? Yes, and that's good. But is it changing humanity for the price tag? No. So, again, this is nuclear weapons research, not nuclear electrical production research. So, yeah, that's where we are. I hope you enjoyed this video. This was way longer than I wanted it to be, but I had to keep pausing to just expressing my disbelief in the last time we talked about nuclear power. This was yesterday with the SL1. I had to keep saying this reactor is a terrible design. In this case, I just have to keep saying nuclear fusion has not been fully achieved ever on Earth except for nuclear bombs. And this was nuclear bomb research. Keep that in mind. So there you go. Enjoy. Love you guys. Have a good one. Peace.